Today, we're diving into the colossal forces that literally build our world, the ones that raise mountains from flat plains and carve out entire oceans. We're talking about the Earth's engine, tectonic plates. And this isn't some ancient history lesson. This is happening right now, deep beneath your feet.
So first things first, let's take a quick look inside our planet. You see, it's not just a solid ball of rock. It's built in layers. Way down at the center, you've got a super hot solid inner core. Around that, a liquid outer core. Then you have the huge mantle, and the very top of that mantle is a hot, semi-molten layer called the asthenosphere. I want you to think of it like incredibly thick, hot tar. Floating right on top of that is the cool, brittle crust, the part we live on. Now here's the kicker. That crust isn't one solid piece. Not at all. It's actually fractured into these massive plates. Which brings us to the big question for today. Is the ground beneath us is always moving? What happens when these enormous chunks of our planet crash into each other, split apart, or just grind past one another? To answer that, we've got to look at the engine that's driving this whole process. This is the incredible idea of plate tectonics, and it's really the grand unifying theory that explains why our planet is so alive and so dynamic. Okay, here's probably the best way to picture it. Imagine the Earth's hard outer shell, we call it the lithosphere, is like a cracked eggshell. Each one of those broken pieces is a tectonic plate, and they are all floating and sliding around on that gooey, tar-like asthenosphere just below. And those eggshell pieces, those are the tectonic plates. They are absolutely enormous, rigid slabs of rock, and they're moving at about the same speed that your fingernails grow. It sounds slow, but when you're talking about this much rock, it's a slow-motion ballet of almost unimaginable power. So what's the engine making them move? Well, it all comes down to heat escaping from the Earth's core. The best analogy is a giant pot of water boiling on a stove. The hot water at the bottom rises, spreads out across the top, cools down, and then sinks again. That exact process, known as convection, is happening right now, on a massive scale, inside the Earth's mantle. And you can see that cycle right here. Hot, less dense rock from deep inside the mantle slowly rises. When it gets near the top, it spreads out, and it literally drags the tectonic plates along with it, kind of like a giant conveyor belt. Then, as that material cools off, it gets denser and sinks back down, completing the loop. This incredible, non-stop cycle is the true engine that shapes our entire world. Okay, now let's get into the action. What happens at the edges where these plates meet? We're going to start with the most dramatic type, convergent boundaries. This is where you get the great collisions. And a key process you need to know here is called subduction. See, when two plates collide head-on, they don't just stop. One of them is often forced to dive, or subduct, underneath the other one, getting recycled back into the immense heat of the mantle. But which plate sinks? Well, it all comes down to a simple matter of density. You've got two types of crust. Oceanic crust, the rock under our oceans, is thin, but it's really heavy. Continental crust, which makes up the land, is much thicker, but it's lighter, more buoyant. So when these two types collide, the denser one always loses. So that dense oceanic plate is forced to dive underneath the lighter continental plate, and this process creates two amazing geological features. First, where the plate bends down, it forms a super deep gash in the seafloor called an ocean trench. At the same time, as that sinking plate melts in the mantle, the molten rock rises up and fuels a whole line of volcanoes on the continent, pushing up massive mountain ranges like the Andes in South America. But what happens when the plates that are colliding are the same type? Well, if two oceanic plates meet, the older, colder, and therefore denser one subducts. This creates an ocean trench and a chain of volcanic islands. But if two continental plates collide, neither one is dense enough to sink. Instead, they just smash into each other, and the only way to go is up. They buckle, crumple, and create absolutely colossal mountain ranges like the Himalayas. And here's a closer look at that ocean-on-ocean collision. As the one plate subducts and melts, that magma punches its way back up through the seafloor, building a whole chain of volcanoes. Over time, these volcanoes emerge from the water, and we get what's called a volcanic island arc. The Aleutian Islands off of Alaska are a perfect example of this in action. So we've seen what happens when plates collide, but what about when they pull apart? That brings us to our next type, divergent boundaries. This is where brand new crust is born. Yep, At these boundaries, the plates are moving away from each other as the crust is literally torn apart. This whole process is called seafloor spreading, and you can think of it like a giant conveyor belt on the ocean floor, constantly churning out new Earth. And the process is pretty straightforward. First, those convection currents in the mantle push the plates apart. Second, magma from below rises up to fill the gap. Third, that magma cools down and hardens into brand new oceanic crust. And finally, this whole process pushes the older crust further and further away, making the entire ocean wider over millions of years. This incredible creative force builds the longest mountain range on our planet, the Mid-Atlantic Ridge, which is almost entirely underwater. Now, when this same splitting happens on land, you don't get a ridge. Instead, it rips the continent apart, forming deep cracks in the earth, called rift valleys, like the Great Rift Valley in East Africa. All right, we've seen plates collide, and we've seen them split. Now for our final type, conservative boundaries. This is where plates just slide right past each other. Now, this is called a conservative boundary, for a simple reason. The crust is conserved. It's not created, and it's not destroyed. Instead, you just have two plates sliding horizontally, grinding against each other along a massive fault line. But that grinding motion is anything but smooth. The edges of the plates get stuck, they lock up, and immense stress and pressure builds up over decades, sometimes centuries. When that pressure finally gets to be too much, it releases in a sudden, violent snap, sending out massive shock waves. And that's what causes powerful earthquakes. The San Andreas Fault in California is probably the most famous example of this in the world. Okay, so let's zoom all the way out now and put all these pieces together to really see the big picture of our incredibly active and ever-changing planet. You see, it all connects into one single, planet-wide system. You can see the new crust being created at the divergent ridge in the middle of the ocean. You see the old crust being destroyed and recycled at the convergent subduction zone. And all the while, these conservative or transform faults are accommodating all that sliding motion. It's a single, interconnected engine, constantly remaking the Earth's surface. So let's just do a quick recap of these powerful forces. Convergent boundaries, the collisions, are the planet's great builders. They give us our deep ocean trenches, massive fold mountains, and fiery volcanic arcs. Divergent boundaries, the splits, are the creators, forming brand new crust at ocean ridges and rift valleys. And finally, conservative boundaries, the grinds, are the shakers, creating the fault lines that trigger powerful earthquakes. These incredible forces built the entire world that we know over hundreds of millions of years, shifting continents, raising mountains, and opening oceans. And they are still hard at work today, which leads us with one really big question. Where are they going to take our planet next?